So, in the series of lectures on calculus, we will first start with function. The first chapter we will deal with is functions. So, let us start functions. Functions. So, what exactly function is? We will not go into the definition of function, but we will surely see what actually function means, and we will see the conditions for some relation to be a function. So, condition for something to be a function. Conditions for function. Conditions should be, the first one is, let us assume there are two sets. There are two sets, two non-empty sets actually, two non-empty sets. Let us name them A and B, namely A and B. Now, the first condition is the set should be non-empty, and the second condition is each element in set A should be mapped with strictly one element in set B. In set B. So, what we are trying to say, we'll see now. And before moving forward and clarifying this point, let us see some notations. So, function from A to B is denoted as function from A to B, where A and B are two non-empty sets, and A is called the domain set of the function, and set B is called the codomain set of the function. Now, let us see what we actually mean when we say that each element in set A should be mapped with strictly one element in set B. So, let us make two sets using the symbol. Let us say that this is set A. It has elements, let us say 5, 6, 7, 8. These are the elements in set A, which is a domain set. We can write it as the domain set, and here we will draw set B, which we will say the codomain set, and let us assume the elements to be alpha, beta, gamma, delta. These are the sets. Now, what we have seen, that each element in set A should be mapped with exactly or strictly one element in set B. So let us start mapping. Firstly, each element in set A should be mapped, and it should be mapped with only one element in set B. So 5, let us map with alpha. 6, let us map with gamma. 7, let us map with beta. 8, let us map with delta. This is 8, this is delta. So, what we have done? We have mapped each element in set A with strictly one element in set B. That is, A has been mapped with alpha. That is, sorry. 5. Element 5 in A has been mapped with alpha. Element 6 in A has been mapped with gamma. Element 7 in A has been mapped with beta. and element A8 has been mapped with delta. So we can see that 5 has been mapped with alpha, so there is only one mapping, that is 5 is mapped with only one element in B. Similarly, all other elements in A have been mapped with only one element in set B. If this is a scenario, then this relation from A to B is called function, and we will represent it by function from A to B. Now we will see some more conditions and where we will check if the relation is actually a function or not. So let us make another set A, another set B. Now let us make it 1, 2, 3, 4, and here we will name them alpha, beta, gamma, delta, phi, let us say. So these are the elements in set B, and these are the elements in set A. Now we will start mapping. Here we have mapped one with alpha, and let us also map one with let's say one with gamma. Now we will map element 2 with beta, element 3 with delta, and element 4 with 5. So 1 has been mapped with alpha and beta. So we can say that 1 has been mapped with 2 elements in B. Yeah, these are the elements in A, these are the elements in B. So 1 has been mapped with alpha and beta, that is 1 has been mapped with 2 elements in B. Similarly, 2 has been mapped with, sorry, this should be your just a minute. So this should be alpha and gamma, not beta. This is alpha and gamma. 2 has been mapped with beta, which means exactly one element in B has been mapped with 2 in A. Similarly, 3 has been mapped with delta, one element, 3 has been mapped with only one element in B, that is delta. Similarly, 4 has been mapped with only one element in B, that is phi. So we can see that although 2, 3, 4, these three elements in set A have been mapped with exactly one element in B, but this element, that is 1 in set A, has been mapped with both alpha and gamma, which is not the condition I have written above. Thus, as element 1 in set A has been mapped with element alpha and beta in set B, that is 2 elements in set B, this relation from A to B is not a function, so we will not say it a function. That's why I have marked it incorrect. This is not a function. We can write that this is not a function. Similarly, we'll move again. So let us see one more scenario which will further clarify our understanding. Again, let us make set A and a set B. Here, let us make the elements 1, 2, 3, 4. And here let us make alpha, beta, gamma, delta. So now let us match 1 with alpha, 2 with beta. Let us map 3 also with beta and 4 with gamma. Now let us see elements in A, elements in B, and number of mappings. So 1 element 1 has been mapped with alpha. Number of mappings is 1. Element 2 has been mapped with beta. Number of mappings is 1. Element 3 has been mapped with beta. Number of mappings is 1. Element 4 has been mapped with gamma, and number of mappings is 1. So you can see that 2 and 3 both have been mapped with beta, but the condition is all the elements in A should be mapped with only one element in B. So 2 has been mapped with only one element in B. 3 has been mapped with only one element in B. So this is a function. We can see that no element in set A is being mapped with two elements in set B. This is the condition. The condition is every element in set A, each element in set A should map with strictly one element in B. So this is being satisfied. Although 2 and 3 are mapping with same element, but they are getting mapped with only one element in B. So the condition is being satisfied that each element in set A is being mapped with only one element in set B. So only one element in set B. 1 is being mapped with alpha, number of mapping is 1. 2 is being mapped with beta, the number of mapping is 1 again. Number 3 is being mapped with beta, the number of mapping is 1 again. 4 is being mapped with gamma, so the number of mapping is 1 again. So all the elements in set A, that is domain set is being mapped with only or strictly one element in set B, that is codomain set. So this is a function. Now let us see one more scenario which will further clarify it. Again, let us assume it to be set A 1, 2, 3, 4, and let us assume it to be set B, where we will see A, B, C, D. Let us assume like this, E. Now 1 is being mapped with A, 2 is being mapped with, let us say, B, 3 is being mapped with, let us say, C, 4 is being mapped with D, and let us also assume an element 5 in set A. And 5 is not being mapped with any element. So here element 5 in A is not being matched with any element in B, not being matched with any element in B, but the condition is every element of A should match with exactly or strictly one element in B, but 5 is not being matched with any element in B. So this is also not a function. This is also not a function. One final criteria we will see. Again, let us assume 1, 2, 3, 4 to be the elements of set A, and again alpha, beta, gamma, delta to be the elements of set B. Now start mapping. 1 with alpha. Let us again map 2 with alpha also. So 1 and 2 are both being mapped with alpha, but element 1 is being mapped with exactly one element in B, and element 2 is also being mapped with exactly one element in B. So this is satisfying the condition for function. Now let us see that 3 is being mapped with beta and 4 is being mapped with gamma. We can see that delta, there is no mapping from any element in A to beta to delta, that is an element in B. So, but if we again look at the condition for a function, every element in A should have exactly one element in B. So the condition is imposed on set A, that is domain of the function. So condition 2, this is the condition 2. If you not remember, this is the condition 2. So condition 2 is imposed on domain set only, that is on set set A only. Condition 2 is imposed on domain set only and not on codomain set. So if condition 2 is imposed on domain set only, then even if some element in codomain set remain unmatched, there is no problem, because the condition is being imposed on set elements of set A, that all the elements in set A should have exactly one mapping with an element in set B, but there is no condition imposed on element in set B. So we can say that if the elements in set A are satisfying the conditions, then it will be a function. So if you see that 1 is being mapped with alpha, similarly 2 is being mapped with alpha again, 3 is being mapped with beta, and 4 is being mapped with gamma. So 1, 2, 3, 4, all the elements have been mapped with exactly one element in codomain set, that is B set. So this is a function. Now let us write the properties of a function, and we will not write anything other than what we have discussed till now. So the properties are: each element in domain set should have strictly one mapping with an element in set B, that is the codomain set. That is, each element in domain set should be mapped with only one element in set B. This is one property. The second property is we can say that two or more elements in domain set can have the same image or same mapping in set B, that is codomain set. Two or more elements in domain set can have the same mapping in codomain set. There is no problem. We can see here. We can see that two elements, 2 and 3, are being mapped with the same element B, beta. So this is all right, as till each element in set A is being mapped with strictly one element in set B. So this point number 2 is completely all right. Third point, we can say that condition 2 is imposed on imposed on codomain on domain set only. On domain set only. Condition 2 is imposed on domain set only. So codomain set can have some unmapped elements. There is no problem. Now we'll see, with the help of some graphical questions, which graph we can say to be a function and which graph we will not say as a function. So before that, let us discuss a very common thing. You would have studied f of x equals to y. This is called a function of x and this is y. Here x is actually the domain of the function. And y is subset of the codomain. You should see this. This is a subset of the codomain, not the codomain itself. And here it is the domain of the function itself. And this subset is called range of a function, which we will discuss later in the videos. We will discuss these things in the subsequent classes. A subset of codomain is called range, which we consider when we write f of x equals to y. Subset of codomain is nothing but the range of the function. Okay, now we'll see some graphical questions. Okay, let us consider a circle with its origin at center and having a radius of, let us say, 1 unit. This is your y, this is your x. Now if this circle is a function, denotes a function or not. This is the question. If this circle denotes a function or not. So let us see. Every x should be mapped with an element in codomain, and y is a subset of codomain. So like we can say that there is x0, x1, x2. These are the domain elements here, and there are a lot of codomain elements, and this y0, y1, y2 are 3 elements inside this codomain. There can be many other elements. So this is called a subset of codomain, that is the range. So this x0, we can see that this element, this x has this value of y. So we can say that yes, if it is x0, let us say this as y0. This x0 has been mapped with y0. All right. Again, if we see this x, then y for this is again this. We can say that x1, for x1, the image is y1. Again, it is mapping with here. Then we can see that for this x0, not only this y0 is there, there is another y just below it, and this is here. So for same x0, we have two y's, that is x naught is being mapped with some another y also. Let us see, let us say that this is y2. So this x naught is being mapped with y2 also. So we have seen that x naught can have just exactly one mapping in codomain, but x naught is being mapped with y naught also, and x naught is being mapped with y2 also. This is not a function. For every value of x, if you see this value of x, then this is one y, and this would be another y. If you see this x, then these two are the two values of y. So for every x, there are two images of x in the codomain. There are two values of y. So let us say x1, x2, x3, like that, y1, y2, y3, y4, something like that. X1 will have some image y1 and y2. Similarly, x1, x2 will have some image y2 and y4. x3 will have some image, let us say y2 and y3. Just we can just an illustration, not strictly consistent with this equation. So we can say that every element in domain is being mapped with two elements in codomain, which should not be the case for a function. So we can say that every element in domain is being mapped with two, that is more than one, with two elements in codomain. So this is not a function. This is not a function. Let us take one more example. Now let us consider a quadrant of a circle. This part only. This is just a part of a circle in the first quadrant. This is y, this is your x. If you see here, every x has been mapped with one y. So every x is being mapped with a y, and every x is mapped with exactly one y. There are not more than one y's for one x. For this x, this is exactly one y. 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 So for each x, that is for each element in domain, there is only one y. So you can say this is the scenario there. If we say x1, x2, x3, so each x1, x2, x3 is being mapped with some y1, y2, y3. If we see, x1 is being mapped with, let us say y1, x2 with y2, x3 with y3. So each x, for each x there is only one element, there is only one y. So this denotes a function. This graph represents a function. This represents a function. This was example 2. Let us say this 2. Let us say this as 1. Let us see some more example on graphs. Take this graph. This is nothing but graph of y equals to modulus of x. So this is the graph for modulus of x. So now if you look for all x, for this x, this is the y value. For this x, this is the y value. Similarly, so let us say this x, this is the y value. for this x, this is the y value. So for every x, we can see that there is only one y value. That is, for every element in domain set, there is only one element in codomain set. So we can say that this is a function. Now you can observe one thing. What you can observe is, if you see this x and let us say some x here, then this x1, let us say, this x0, let us say. So let us say this is x0, this is x1, and both have same y value. Y, let us say this point to be some y naught only. So this is y naught. So x0 is being mapped with y naught, and x1 is also being mapped with y naught. But the condition that every element in domain should have exactly one element in codomain, or every element in domain should be mapped with only one element in codomain, is being satisfied. x0 is mapped with only one element, that is y naught. x1 is mapped with only one element, that is y naught. Similarly, all other x have been mapped with only one value of y. So this is a function. Now we can, if we reverse the case, let us see this condition. This is nothing but a parabola. This is y, this is your x. Now let us see for each x. For this x, this is one of the y values, and this is another y value. So if this is x1, this is y1, this is y2. Similarly, for this, let us say x2, this is one value, and this is another value. So we can see that for one x, let's say this one x1, there are more than one elements in codomain. x1 is being mapped with y1 also and y2 also. So we'll say this is not a codomain. This is not a function, or this graph does not represent a function. Another one, if we like to see, let us take the portion of the graph in the x-axis only, this much graph only. This is your y, this is your x. And now if you see, for every x, there is only one y. For every x, there is only one y. For every x, there is only one y. So all the x values are mapped, and for every x value, there is only one y. So this is a function. So this is how we can interpret which conditions will satisfy a relation to be a function, and where they will not satisfy the condition of being a function. So with this, I'll end the class today. From tomorrow, we'll see more on domain, ranges, and codomain. So thank you.